Good morning, everybody. I welcome you all to this series of lectures on electronic devices and circuits. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE, Dundigal. Today I am going to discuss on definition and terminology for diode applications. Definitions and terminology for diode applications. So, for the first question is define PN diode and mention its characteristics. So, what is a PN diode? It is a basic semiconductor device that controls the flow of current in the circuit. And it contains two types of characteristics, the forward and the reverse characteristics. It essentially consists of two types of materials, P material and N material, and these two materials are joined together and ohmic contacts are made at the ends, and that is how the PN junction is formed. So, it controls the flow of current in a circuit. When the PN junction diode is forward biased, that means when you apply a positive voltage to P and negative voltage to N, we know that the PN junction diode is forward biased and it acts like a closed switch. So, in forward bias condition, it allows the flow of current liberally. And when the PN junction diode is reverse biased, that means when we apply a negative voltage to P and positive voltage to N, it is reverse biased and it acts like an open switch. So, practically no current flows. And the PN junction diode characteristics are like this. So, in the forward direction, there is a more current. So, this is more. So, this is the current I and this is the voltage V across the diode. And I is the current through the diode. And when it is reverse biased, that means when the voltage is negative, very less current flows, and that is nothing but the reverse saturation current. Next, what is static resistance, and write the expression. See, the static resistance is calculated by taking the voltage and at that point of voltage taking the current. So, that gives the DC or the static resistance. So, when we take the diode for characteristics like this, so this is a voltage V and this is a voltage, this is a current I. And let us say this point is Q. And at this point, we note down the voltage, and at this point, we note down the current. So, because this is a forward characteristic, we have added a suffix F. So, at this point, the voltage is Vf and the current is If. So, the static resistance Rf is given by Vf by If. Please note that the static resistance, it is not constant, and as the operating point moves across this forward characteristic, the static resistance varies. Next, what is the dynamic resistance, and write the expression. So, dynamic resistance is determined by drawing a straight line between the two intersections of maximum and minimum values of input voltage and then finding out the difference in current. So, it is calculated like this. This is a voltage V and current I through the diode. So, let us take these points which are close by, and a tangent line is drawn, and we calculate what is the difference in voltage across these 2 points, and we also take the difference in current across these 2 points, and this is called as del IF and this is called as del VF. So, the dynamic resistance RF is given by del VF by del IF. That is the dynamic resistance. what is a drift current in a PN diode? So drift current, it is a current which is caused by the application of voltage. So because when the applied voltage is more than the barrier potential, then there is going to be a flow of current through the diode, and the current which is caused by applying the external potential is called as the drift current. So drift current is the electric current or movement of charge carriers which is due to the applied electric field. So it is also called as electromotive force over a given distance. Define electronics. In the name itself we have electrons. So the flow of electrons which deals with the conduction of current through vacuum or gas or through a semiconductor. So that is how the electronics is defined. State conductivity, it is the opposite of resistance. So conductivity is the ability of the metal to conduct electricity when a potential difference is applied. So if a material is having very less resistance, naturally the conductivity is more. If the material is having more resistance, the conductivity is less. Next, define voltage and mention its units of voltage. So the unit of voltage is volts. This is current, resistance. So what is a circuit? A circuit is a collection of real components, power sources and signal sources, and all connected. So current can flow in complete loop. So that is a circuit. Define conductor and write few examples. See, materials are basically classified into three types. We have the metals, metals, and insulators and semiconductors. So metals are also called as the conductors, and a conductor is a material which has a very high value of conductivity. Examples are copper, aluminum, and silver. See, basically the conductor or metal, it is characterized by the overlapping of valence and conduction bands. So if you take the energy band structure of metal, so this is the valency band, I call it as EV, and this is the conduction band, I call it as EC. And the gap between conduction band and valence band is called as the forbidden energy gap. So in this case, the forbidden energy gap is given by EC minus EV. So naturally, for a metal or for a conductor, it is negative. Next, define semiconductor and write few examples. So semiconductor, it is a material which has conductivity that lies between insulator and conductor. Examples are silicon and germanium. So they have the conductivity which lies between insulator and conductor, and examples are silicon and germanium. If you see the if you see the forbidden energy gap for the semiconductor, it is roughly 1 electron volt. So this is the energy band structure for the semiconductor. This is the conduction band EV, and this is energy band EC. This is a valency energy level, and this is a conduction band energy level. So the forbidden energy gap is given by EC minus EV, and for a semiconductor it is roughly 1 electron volt. For a semiconductor it is roughly 1 electron volt. So semiconductor is a material that has conductivity which lies between the insulator and the conductor, and examples are silicon and germanium. What is an insulator? It is it is on the other extreme. So it is a material that offers a very low level of conductivity when voltage is applied. Examples are wood and glass. That means insulator has a very large forbidden energy gap, roughly about 6 electron volts. The energy band structure of the insulator is like this. The conduction band EC, and this is the valency band. You see the forbidden energy gap is very high. Equal to EC minus EV. It is roughly 6 electron volts. So you need to put a lot of effort, or you need to apply a lot of energy to move the charge carrier from valence band to the conduction band. So that is why practically no current flows through the insulator, and we say that the conductivity of the insulator is 0, or resistance of the insulator is infinity almost. Now, drift current, it is nothing but the current because of the applied electric field. And define intrinsic semiconductor and write few examples. What is intrinsic semiconductor? It is a pure form of semiconductor, and we call it as intrinsic semiconductor. So intrinsic semiconductor, it has typically 4 valence electrons in the outermost orbit. So for silicon, there are 4 valence electrons in the third orbit. Whereas for germanium, there are 4 valence electrons in the fourth orbit. That is the difference. But for both cases, we have only 4 valence electrons, and these are called as intrinsic semiconductors. Why they are called intrinsic? Because the number of holes is equal to the number of electrons in intrinsic semiconductor. Examples are silicon and germanium. Define extrinsic semiconductor. So extrinsic semiconductor, it is a material where the number of electrons is not equal to the number of holes. So by adding impurities, the intrinsic semiconductor is made extrinsic semiconductor by adding proper dopants. So for p-type impurities, for the n-type impurities, the dopants which are used are phosphorus, bismuth, arsenic, and antimony. These are used to convert intrinsic semiconductor to n-type extrinsic semiconductor. And p-type dopants are boron, gallium, and indium. These are the dopants which make the intrinsic semiconductor to p-type. And other important characteristics of these n-type dopants are they are pentavalent atoms. These are pentavalent. These are pentavalent, which means that they have 5 valence electrons. Coming to the p-type, boron, gallium, and indium, these are trivalent. So that means they have 3 valence electrons in the outermost orbit. Now define diffusion current. It is a current in a semiconductor which is caused by the diffusion of charge carriers because of the difference in the concentration gradient. So this is a current which is due to the transportation of charges occurring because of the non-uniform concentration of charged particles in a semiconductor. Suppose if you take a semiconductor bar, p-type bar, and let us say it is non-uniformly doped. That means we have more holes here. We have more holes here, let us say. And let us say we have less holes. So as you see here, on the left hand side you have more holes, and on the right hand side you have less number of holes. So the hole distribution is not uniform. In such a case, what happens? These holes move from high concentration area to the low concentration area. So this causes flow of charge carriers, and whenever there is a flow of charge carriers, we say that diffusion current comes into picture. So there is a diffusion current. So diffusion current essentially is because of the concentration gradient, or it is because of the non-uniform distribution of charge carriers which causes this diffusion current. So it is a current in a semiconductor caused with the diffusion of charge carriers, and this is the current which is due to the movement of charges because of the non-uniform distribution of charge particles. Now, what is a capacitance? So, capacitance is the ability of the component or circuit to collect and store energy in the form of electrical charge. And what is the formula for capacitance? C is equal to Q by V. Q is the charge and V is the voltage. So, it is the ability of the component or circuit to collect and store charge in the form of electrical charge. Next, define diffusion capacitance and write the expression. So diffusion capacitance, it is a capacitance due to the transportation of charge carriers because of concentration gradient, and it occurs between the two terminals of a device, and the formula is dq by dv. So in a PN junction diode, if you apply a forward bias, what happens? The depletion layer width, it reduces. So there is going to be change in the charge carriers with applied external voltage. So whenever there is a change of charge with voltage, we have a capacitance effect. So diffusion capacitance, it is a capacitance due to the transportation of charge carriers between the two terminals of a device. And for a diode, we define diffusion capacitance during the forward bias. And we have derived in it that the diffusion capacitance CD is given by eta Vt by I. I is the current and eta is the constant, and eta is equal to 1 for germanium and eta is equal to 2 for silicon, and Vt is the voltage equivalent of temperature. So CD is the diffusion capacitance. So for a diode, we define diffusion capacitance during the forward bias, and CD is given by eta Vt by I. Next, define diffusion capacitance and write the expression. So the amount of capacitance that changes with increase in voltage during reverse bias, that is called as the transition capacitance. So if you take a diode, when you apply a reverse bias, what happens? The depletion layer width, it increases. So the more and more reverse voltage you apply, the more and more the number of charge carriers, or the moment, or the ions, they increase at the junction. So the junction width increases will increase in the reverse bias. So this is nothing but the transition capacitance, and the transition capacitance per diode is given by this formula: Ct is equal to epsilon A by D. D or W. W is the space charge region width, or it is the width of the depletion region. Next, what is a load line? See, load line, it is a line that is drawn on the characteristic curve, that is graph of the current versus voltage in a nonlinear device like a diode. So that's a line drawn on the characteristic curve. Suppose you take this circuit having the diode like this. So this is a diode, and let us say this Vi is the input voltage, and Vf is the output voltage, and this is the resistor R, and let us say the current in the circuit is If. Because the diode is forward biased, we take the current is If. So if you apply the KVL law to this circuit, you get Vi equal to IFRF plus Vf. So we write Vf equal to Vi minus IFR. So what is the VI characteristic of the diode? It's like this. The VI characteristic of the diode, on the x-axis we take the voltage V, and on the y-axis we take the current If. So on the characteristic curve, we draw the load line. So to draw a line, how many points are required? We need 2 points. Now let us assume that Vf is equal to, Vf equal to 0. So if Vf is equal to 0, what we get? If is equal to Vi by R. So you have got one point. What is the point? 0, comma Vi by R. This is one point. Next, you assume If equal to 0. So if If equal to 0, then you get Vf is equal to Vi. So you substitute these values in equation 1. First you assume that Vf equal to 0, then you get If is equal to Vi by R. Then you assume that If equal to 0, then you get Vf is equal to Vi. So the second point is Vi, comma 0. So let us put these points on this curve. So here you are getting Vi, comma 0, and here you are getting 0, comma Vi by R. So when these 2 points are joined, you get a straight line, and the intersection of the load line with the characteristic curve is called as operating point, or the Q point, or the quiescent point. That is a load line. Define storage time. So the time period for which the diode remains in the conduction state, even when the reverse biased state, is called as the storage time. So when you apply a reverse bias, the diode should come into non-conducting state. But for a small amount of time, it remains in the conduction state. So that time is called as the storage time. Define the transition time. The time that is elapsed in returning back to the state of non-conduction, that is steady state reverse bias, that is called as the transition time. So it is the time taken for the component to change from one state to another state. So that is the transition time. State forward recovery time in diode switching times. So this is the time that is required for the diode to change from the reverse bias to forward bias, and that is called as the forward recovery time. Now state the reverse recovery time in diode switching times. So this is the time required for the diode to change from forward bias to reverse bias, and that is called as the reverse recovery time. What is a rectifier? And list the types of rectifiers. It is a circuit that converts AC voltage of main supply into the DC voltage. So that is called as rectifier. But you don't get perfect DC, you get some AC components. So we say that voltage is called as pulsating DC. So rectifier, there is a circuit which converts the AC voltage of main supply into the pulsating DC voltage. There are three types of rectifiers: half-wave rectifier, full-wave rectifier, and the bridge rectifier. And half-wave rectifier is like this, which employs just one diode, and it gives only one half of the input cycle. And full-wave rectifier, it rectifies both cycles of the input wave, and it uses two diodes. And also it uses the center tap transformer. The center point is grounded. Load resistor is connected here, like this. This is a full wave rectifier. Of course, I have not drawn the secondary, primary transformer. And the bridge rectifier, it has four diodes. The four diodes are like this. The input is applied here, and the output is applied. The output is taken across this load resistance RL. The main advantage of bridge rectifier is the PIV voltage is only Vm, but in full wave rectifier the voltage is 2 Vm. So you need to use the diodes with higher rating in the case of full wave rectifier. Bridge rectifier overcomes this disadvantage because it uses 4 diodes. So the peak voltage 2 Vm is shared between 2 diodes. So the peak inverse voltage is Vm in the case of bridge rectifier. Define peak inverse voltage in rectifiers. So it is a voltage which appears across the diode when it is reverse biased. So there is a peak inverse voltage. For a half wave rectifier it is Vm. For a full wave rectifier it is 2 Vm. For a bridge rectifier it is Vm. So peak inverse voltage, it refers to the maximum voltage of a diode which appears in the reverse biased condition. Define ripple factor related to rectifiers. It is defined as the ratio of RMS AC component to the DC component in the rectifier, and that is called as the ripple factor. And ripple factor, it indicates the performance or the merit of the rectifier. So if more the value of ripple factor, that means the rectifier is inefficient. It has more AC components. That means the DC output, it is not smooth. So the output voltage is not smooth if the ripple factor is more. If the ripple factor is 0, that means the output is a perfect DC. So it indicates the quality of the output from the rectifier. The ratio of RMS value of AC component to the DC component in the rectifier circuit is called as the ripple factor. Rectifier efficiency. It is a ratio of DC power obtained at the output to the applied AC input power that is called as the rectifier efficiency. So DC power output divided by the AC input power that is called as the rectifier efficiency. Define clipper. So clipper is a circuit that is designed to prevent a signal from exceeding a predetermined reference voltage level. That is nothing but a clipper. And if you are clipping the positive portion of the input signal, it is called as the positive clipper. And if you are clipping the negative portion of the input signal, that is called as the negative clipper. So clippers are currently classified. We have a series clippers and we have the shunt clippers. In series clippers, the diode is in series with the input voltage. In shunt clipper, the diode is in shunt with the input voltage. So positive series clipper circuit is like this. This is a positive series clipper. So what this essentially does, it clips the positive portion of the waveform. If the input signal is like this, the output is going to be like this. So you can see it is perfectly removed the positive portion. And if you apply a reference voltage, then you get clipping at defined levels as per the requirement. So you also have the positive series clipper with positive reference voltage, positive series clipper with negative reference voltage, and positive shunt clipper is like this. This is a positive shunt clipper. So this circuit also, when the input is positive, the diode is forward biased and it acts like a short circuit and you don't get any output. And when the input is negative, then the diode is reverse biased and whatever input voltage you apply, it appears across the output. So this is a positive shunt clipper. And accordingly, we have positive shunt clipper with positive reference voltage, positive shunt clipper with negative reference voltage. And coming to the negative series clippers, the circuits are same, only the polarity of the diode is changed. So these are the clipper circuits. So what is a biased clipper? So biased clipper is a clipper when a small portion of the positive or negative half cycles of the input voltage are removed. So these are called as the biased clippers. Define cutting voltage. So when the diode is forward biased, for small applied input voltages you don't get current. So when you increase the voltage slowly, only when the applied input voltage is more than the cutting voltage, then only the current flows through the circuit. So that is called as the cutting voltage. So the forward voltage at which the current to the junction starts increasing rapidly, that is called as the knee voltage or the cutting voltage. Now define clamper circuit using PN diode. A clamper, it is a circuit which changes the DC level of the input signal. Clamper circuits, they use energy storage devices like capacitor. Next, let us see the circuit of positive clamper. So we use a capacitor, then we use diode, and this circuit, what it does, it moves the waveform upwards and if you apply a DC signal with average value 0, the DC value goes up and it becomes positive. So this is the positive series tripper. State the definition of positive clamper using the diode. So a positive clamper is a circuit that consists of diode, a resistor and a capacitor that shifts the output signal to the positive portion of the input signal. And what is a negative clamper? A negative clamper, it does the opposite. It consists of a diode, resistor and a capacitor that shifts the output signal to the negative portion or below the zero level. That is a negative clamper. What is the clamping circuit theorem? So this theorem, it states that under steady state conditions for any input waveform, the ratio of the area under the output voltage curve in the forward direction to that in the reverse direction, it depends upon the ratio RF by R, where RF is the diode forward resistance and R is the resistance which is connected in the circuit. That is a clamping circuit theorem. And diode comparator. A comparator is a device that compares the two voltages or currents and outputs a digital signal indicating which is larger. It compares, basically it compares. What is a regenerative comparison? What is a regenerative comparator? Regenerative comparator is a circuit that uses positive feedback. And what is a non-regenerative comparator? Non-regenerative comparator is a circuit that uses a negative feedback. What is doping, and list the types of materials? So doping is a process of adding impurities which convert the intrinsic semiconductor to extrinsic semiconductor. We have discussed that if you have to convert to N-type, you have to use phosphorus, bismuth, arsenic and antimony. If you have to convert it into P-type, you have to use boron, gallium and indium. So that is the process of converting the intrinsic semiconductor to the extrinsic semiconductor. So with this, we conclude the discussion of definition and terminology for the unit 1, that is the diode applications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.